At 14,000 feet over the North Sea on February 3, 1944, a B-17 flying fortress named Devil's Own was 4 hours into a bombing mission to Bremen when the number 3 engine exploded. Not failed, exploded. The cowling peeled back like a torn can. Pieces of engine compartment flew past the waist gunner's windows. Fire erupted from the nacelle, fed by high-octane aviation fuel and 200-mile-per-hour winds at altitude. The orange flames stretched back 15 feet behind the wing, visible to every aircraft in the formation. The pilot, Captain James Morrison, hit the feathering button to stop the propeller and shut off fuel to the dying engine. Standard procedure, drilled into every B-17 pilot from their first day of training. Should have worked. Didn't. The propeller kept windmilling. The blades continued spinning in the slipstream, driven by the 200-mile-per-hour wind. The engine kept burning. The fire kept spreading toward the main wing spar and the fuel tanks that held 2,180 gallons of 100-octane gasoline. Morrison could see the paint bubbling on the wing surface, could see the aluminum skin starting to discolor from heat. The wing was beginning to fail structurally. Morrison had maybe 90 seconds before the wing burned through and the aircraft broke apart. He ordered the crew to prepare to bail out. 10 men started grabbing parachutes in a bomber that was losing altitude, on fire, deep over enemy territory in February. The North Sea below them was 42 degrees. Survival time in that water was measured in minutes. Even if they survived the bailout, even if they avoided German fighters and flak, the odds of rescue were nearly zero. Morrison knew it. His crew knew it. This was how B-17s died. What Morrison didn't know was that 40 miles away, at an 8th Air Force maintenance depot in East Anglia, a technical sergeant named Frank Zaremba had already figured out why bombers like Devil's Own were exploding, had already designed a solution, had already installed it on 47 aircraft. But Morrison's bomber wasn't one of them. Devil's Own had arrived at the squadron 3 weeks earlier, transferred from another group. Nobody had modified it yet, and now Morrison and his crew were about to pay the price for flying an unmodified aircraft. The B-17 engine explosion problem killed approximately 120 American aircrews between November 1943 and March 1944. Not 120 men, 120 complete crews. That meant somewhere between 1,080 and 1,200 individual airmen, depending on crew configurations. The Army Air Force knew about it. They documented it extensively. They studied it with engineering teams. They wrote detailed reports about it. They convened review boards. They interviewed survivors. They examined wreckage. But they couldn't fix it. The problem was maddeningly specific. It only happened under certain conditions. High-altitude operations, typically above 12,000 feet. Combat damage to the engine, usually from flak or cannon fire, followed by attempted feathering of the damaged engine. When those 3 factors aligned perfectly, engines didn't just fail gracefully. They detonated with the force of a bomb. The detonation usually ignited fuel lines, which ignited wing tanks, which caused catastrophic structural failure. Bombers went from controlled flight to falling debris in under 2 minutes, sometimes faster. The official explanation from Army Air Force headquarters was battle damage. Enemy fire compromised engine components, leading to secondary failure. It made sense on paper. Flak hits engine, engine breaks, fire starts, airplane crashes, combat loss. Tragic but unavoidable. Crew chiefs were told to inspect engines more carefully during pre-flight checks. Pilots were told to feather damaged engines immediately, not to wait. Maintenance schedules were tightened. inspection intervals were reduced. None of it worked. Bombers kept exploding at the same rate. The problem wasn't random. Lieutenant Colonel David Chen, operations officer for the 351st Bomb Group, noticed the pattern in December 1943. He'd been tracking combat losses for his group, trying to understand why they were losing so many aircraft. The numbers didn't make sense. The 351st was losing bombers at a higher rate than other groups in the same wing, flying the same missions, facing the same defenses. Chen pulled mission reports going back 4 months, found 11 cases where B-17s had exploded after taking engine damage. All 11 followed the same sequence: engine hit by flak, pilot attempts to feather, explosion within 30 seconds, aircraft lost with all crew. Chen wrote a report, sent it up through channels. The report noted the pattern, suggested there might be a systemic problem with the feathering mechanism, recommended engineering investigation. The report reached 8th Air Force Headquarters in January 1944. An engineering staff officer reviewed it, noted that the sample size was too small for statistical significance, concluded that the losses were within expected parameters for combat operations. No investigation was ordered. Chen's report went into a file cabinet, but Chen wasn't the only one noticing. Maintenance officers at 3 different bomb groups had identified the same pattern independently. All 3 wrote reports in December and January. All 3 reports went through channels. All 3 disappeared into the administrative machinery of 8th Air Force Headquarters. The problem was that nobody at headquarters was connecting the dots. The reports came from different groups, went to different staff sections, landed on different desks. Nobody was looking at the aggregate data. Technical Sergeant Frank Zaremba didn't have access to aggregate data. He had something better. He had a mechanic's eye and a memory for details. Zaremba had been maintaining B-17s since August 1943, 9 months of working on the same aircraft type every single day. He'd worked on bombers at Burton Wood Depot, where damaged aircraft came for major repairs. Then at Bassingbourn Airfield, where he maintained operational aircraft for the 91st Bomb Group. Now he was at a forward maintenance facility designated Station 174, a small field in East Anglia, where aircraft went for quick turnaround between missions. Zaremba had seen 6 bombers lost to engine explosions by January 1944, had read the accident reports when they were available, had talked to surviving crew members when there were survivors, had examined wreckage when there was wreckage to examine, which wasn't often because aircraft that exploded in flight didn't leave much wreckage worth examining. But Zaremba paid attention to details other people missed. He noticed that the explosions always happened after feathering attempts, never before. That meant something. The B-17's Wright R1820 Cyclone engine was a 9-cylinder radial design producing 1,200 horsepower at 2,500 RPM. It was a proven engine, reliable, with thousands of flight hours across multiple aircraft types. The B-17, the C-47 transport, even some Navy patrol aircraft used variants of the same basic engine. The engine itself wasn't the problem. Zaremba knew that. The problem was what happened when you tried to shut it down after combat damage. Feathering a propeller means rotating the blades to align with the airflow, eliminating drag. A windmilling propeller creates enormous drag, slows the aircraft, makes it harder to maintain altitude. Feathering is essential after engine failure. The mechanism works through oil pressure. The feathering system uses engine oil, pumped under pressure through lines running from the engine-driven oil pump to the propeller hub. When the pilot hits the feathering button in the cockpit, a valve opens. Oil flows into the hub through a rotating seal. The oil pressure acts on a piston mechanism inside the hub. The piston rotates the blade pitch change mechanism. The blades rotate to the feathered position, typically around 90 degrees from their normal operating angle. A lock engages to hold them in place. Takes about 8 seconds under normal conditions. But combat damage changed everything. A single 20mm cannon shell or a piece of flak shrapnel hitting the right spot could fracture an oil line without severing it completely. The line would develop a crack, maybe a quarter-inch long. The crack would leak, but the line would maintain enough pressure for normal operation. The engine would keep running because the oil pump could compensate for the small leak. Instruments would show oil pressure dropping slowly, maybe 5 pounds per minute, not catastrophically. The pilot might not even notice immediately. Oil pressure gauges on the B-17 were mechanical, prone to sticking, and pilots were monitoring dozens of other instruments while flying formation through flak. Then came the feathering attempt. When the pilot hit the feathering button, the system demanded maximum oil pressure. The pump worked harder to overcome the resistance of the blade pitch change mechanism. Pressure in the line spiked from the normal 60 psi to over 200 psi. The fractured line, already weakened by the initial damage, would rupture completely under the surge. Hot engine oil at 180 degrees Fahrenheit would spray under pressure directly onto the magneto system. The magnetos were the heart of the ignition system, 2 magnetos per engine, mounted on the rear accessory case, generating electrical current for the spark plugs. They operated through magnetic induction, spinning permanent magnets past wire coils to generate high voltage, several thousand volts. The magnetos ran hot, typically 250 to 300 degrees during operation. They were designed to handle heat. They were not designed to handle hot oil spray. Hot oil hitting live electrical components at high voltage created arcing. Electrical discharge jumping through the oil mist. The arcing ignited oil vapor. The oil vapor ignited residual fuel in the carburetor intake. The carburetor was mounted directly below the magnetos, connected by the intake manifold. An explosion in the carburetor would rupture fuel lines. The fuel lines on the R-1820 carried fuel at 15 psi from the wing tanks to the engine. Rupturing those lines released fuel directly into the engine compartment where everything was already on fire, and then everything went to hell. The sequence took less than 10 seconds from feathering button press to major fire, maybe 30 seconds from major fire to wing structural failure. Pilots didn't have time to react. By the time they realized the feathering attempt had gone wrong, the fire was already out of control. Some crews tried to fight it with onboard fire extinguishers. The B-17 carried 2 carbon dioxide extinguishers, one in the radio room, one in the cockpit. They were useless against fuel fires in 200-mile-per-hour wind. The fire would blow out momentarily when hit with CO2, then reignite immediately. Several pilots reported trying to extinguish engine fires, watching them go out, then watching them come back worse than before. Zaremba pulled maintenance records for every B-17 that had suffered engine explosions. He didn't have official authorization. He just started collecting paperwork. Maintenance logs, mission reports, accident summaries, anything he could find. Cross-referenced them with combat reports from the groups that had lost aircraft. Interviewed crew chiefs about pre-flight conditions on the aircraft that had exploded. The pattern was clear. The aircraft were mechanically sound before missions. The engines passed all inspections. Oil pressure was normal during pre-flight checks. Nothing suggested imminent failure. The damage happened in combat, but the explosion happened during the emergency procedure meant to prevent further damage. On January the 12th, 1944, Zaremba requested permission to examine the feathering system in detail. His commanding officer, a major whose name appears in no official records, told him the problem was battle damage, not mechanical failure. Nothing to examine. Zaremba tried to explain the pattern he'd found, explained why normal battle damage wouldn't cause this specific failure sequence. The major wasn't interested, told Zaremba to focus on keeping operational aircraft flying, not investigating theories. The 8th Air Force needed mechanics turning wrenches, not playing detective. So Zaremba did what mechanics do when officers won't listen. He investigated anyway, started working on it during his off hours. Station 174 operated around the clock during heavy mission periods, but there were quiet times. Early morning before the first missions launched, late evening after the last bombers returned. Zaremba used those hours. The feathering system on the right cyclone used a single oil line running from the engine-driven oil pump to the propeller hub. Quarter-inch steel tube, rated for 300 psi, standard aviation plumbing. The line was routed along the top of the engine nacelle, behind the cowling, secured with clips every 18 inches. Nothing unusual about the routing. It followed standard Lockheed design practices, but Zaremba noticed something nobody else had looked for. The line ran within 3 inches of the magneto assembly. 3 inches doesn't sound like much, but at altitude, with the engine running, everything in that nacelle was moving, vibrating, expanding and contracting with temperature changes. The oil line was steel. The engine mount was steel. The magneto housing was aluminum. Different materials, different thermal expansion rates. During operation, that 3-inch gap could shrink to 2 inches or less. When oil sprayed from a damaged line under 200 psi of pressure, it hit the hottest part of the electrical system. The solution was almost stupidly simple. Reroute the oil line away from the magnetos, add 6 inches of separation, move it lower in the nacelle where it would be protected by the engine block. That's it. Simple fix. But there was a problem. The standard oil line wasn't long enough to make the revised routing work. Zaremba measured it carefully. The original line was 34 inches from pump fitting to propeller hub connection. The revised routing would need 45 inches. He needed to add 11 inches of line length. That required a splice. Splicing a pressurized oil line wasn't standard procedure. It violated multiple technical orders about maintaining system integrity. Engine oil systems were supposed to use continuous lines whenever possible to minimize potential leak points. But a splice was the only way to make the rerouting work without fabricating an entirely new line, which was beyond what a field maintenance facility could do. Zaremba needed a threaded union fitting that could handle 300 psi without leaking. The depot had union fittings. They were used in the hydraulic systems for landing gear and flight controls. Quarter-inch thread, steel construction, rated to 500 psi. But using hydraulic fittings in an engine oil system wasn't approved. Different specifications, different applications, different material certifications, different approval requirements. The hydraulic fittings used a different thread pitch. They required different torque specifications. Using them meant cross-threading systems that weren't designed to work together. On January 18th, Zaremba pulled a hydraulic union from the parts bin. Standard AN815 4D fitting, Army-Navy specification, used on thousands of aircraft. Cut an 11-inch section of quarter-inch steel tubing from salvage stock. Steel tube pulled from a damaged B-17 that had ground-looped on landing. The tube was bent, but the walls were intact. Zaremba cut a straight section, cleaned it, flared both ends using the standard flaring tool, fitted it with AN8118 4D flare nuts, assembled the splice on his workbench. Then came testing. Bench tested it for leaks at 350 psi using the hydraulic test stand normally used for landing gear components. Watched for any seepage around the threads. No leaks. Let it sit under pressure for 30 minutes. Still no leaks. Cycled the pressure up and down 20 times. No leaks. The fitting held. Zaremba installed it on a B-17 designated patches that had just returned from a mission with battle damage to the No. 2 engine. The aircraft needed an engine change anyway. Perfect opportunity to try the modification without risking an operational aircraft. The rerouted oil line ran 6 inches lower than the original routing, well clear of the magnetos, protected by the bulk of the engine block. Installation took 43 minutes, including time to fabricate mounting clips for the new routing. Zaremba signed off the modification in his personal notebook, but not in the official maintenance log. If the modification failed, if the splice leaked or burst during flight, he wanted the responsibility on himself, not on the crew chief who would sign the aircraft back to flight status. That crew chief was a friend. Zaremba wasn't going to hang him for an unauthorized modification. Patches flew again on January 22nd. Mission to Wilhelmshaven, a port city on the North Sea. The mission was routine until the bomb run. Flak over the target was heavier than intelligence had predicted. Patches took multiple hits. No. 2 engine, the one Zaremba had modified, took shrapnel through the cowling. Oil pressure started dropping. The pilot, Lieutenant Raymond Tucker, waited until pressure fell below 40 psi, then hit the feathering button. The propeller feathered normally. No explosion, no fire. The engine shut down cleanly. Patches made it home on 3 engines, landed safely. Tucker wrote in his mission report that the No. 2 engine had performed perfectly despite battle damage. The crew chief examined the engine after landing, found the shrapnel damage, found oil leaking from a cracked oil line fitting, not from Zaremba's splice. The splice had held perfectly. The crew chief found Zaremba in the maintenance area that evening, asked him what he'd done to the engine, asked why an engine that should have caught fire hadn't. Zaremba showed him the rerouted oil line, explained the problem with the original routing, explained why moving the line away from the magnetos prevented the explosion sequence. The crew chief looked at it for a long moment, then asked if Zaremba could do the same modification to 3 more aircraft in his section. Zaremba said yes, but told him there could be consequences if any one official noticed, told him they could both face court-martial for unauthorized modifications to flight-critical systems. The crew chief said he didn't care. He'd lost 2 pilots in his section to engine explosions in the past month. If there was something that could stop it, he wanted it. Regulations could wait. By February the 1st, Zaremba had modified 22 aircraft. Word spread through the maintenance crews the way word always spreads among enlisted men. Quietly, during smoke breaks, during chow, mechanics talking to other mechanics. Some refused to do unauthorized modifications, didn't want the risk, didn't want to violate regulations. Others saw the logic immediately, saw that the modification made sense, saw that it was working. They started rerouting oil lines on their assigned aircraft. Zaremba provided the fittings, showed them the routing, emphasized the importance of pressure testing for leaks before signing off the work. Some mechanics fabricated their own union fittings from salvage parts. Others used the hydraulic fittings like Zaremba did. The modifications spread across 3 bomb groups operating from Station 174, the 381st, the 381st, the 457th. No documentation in official maintenance logs, no approval from engineering, just mechanics trying to stop bombers from exploding. The statistics told the story that official reports missed. In January 1944, the 3 bomb groups at Station 174 flew 847 combat sorties. They lost 9 B-17s to engine fires following combat damage, 9 complete crews, 90 men. In February, after roughly 40% of the fleet had been modified, they flew 923 sorties, lost 2 aircraft to engine fires. Both were unmodified aircraft. By March, nearly every operational bomber at Station 174 had the rerouted oil line. They flew 1,156 sorties that month, lost 0 aircraft to engine explosions despite heavy combat operations over Germany. Other bases started noticing something strange. B-17s from Station 174 were surviving engine damage that would have destroyed bombers from other units. Same missions, same targets, same flak defenses, but different survival rates. Intelligence officers thought the crews from Station 174 were getting lucky, thought maybe the German flak gunners were having an off month. Maintenance officers thought Station 174 had better mechanics, better pre-flight procedures, tighter inspection standards. Nobody looked at the oil lines. The modification was invisible unless you opened the cowling and knew what the original routing looked like, and nobody was looking because nobody knew there was anything to look for. The official accident report still said battle damage. The engineering analysis still said pilot error or combat loss. The system wasn't designed to catch unauthorized field modifications that actually worked. Then came the incident that forced official attention. On March 8, 1944, a B-17 named Sharon D, flying with the 351st Bomb Group, took catastrophic flak damage over Berlin. The mission was part of the massive daylight raid on the German capital, 600 bombers, facing some of the heaviest flak defenses in Europe. Sharon D caught a direct hit from an 88mm shell. Number 4 engine took the blast. The entire front of the nacelle was torn open, oil lines severed, fuel lines damaged. The engine should have exploded immediately. Instead, the pilot, Captain Harold Weber, hit the feathering button. The propeller feathered cleanly. No explosion, no fire. Sharon D dropped out of formation, losing altitude but under control. Weber nursed the bomber back across Germany on 3 engines, made it to Belgium before running low on fuel, landed at an emergency field. All crew survived. Weber wrote in his mission report that the engine damage should have caused catastrophic fire. He'd seen other bombers explode from similar hits. He questioned why Sharon D hadn't, requested maintenance investigation to determine why his aircraft had survived when others hadn't. The report went up through channels, reached an engineering officer at 8th Air Force Headquarters. The officer, a major named Robert Kemp, flew out to examine Sharon D. Kemp, was a Cornell-trained mechanical engineer serving his 3rd year with the Army Air Force. He'd investigated dozens of aircraft accidents. He knew what to look for. He examined the damaged engine, found the rerouted oil line, noticed immediately that the routing was non-standard, traced it back through the nacelle, found Zaremba's splice, recognized that someone had modified the system deliberately. Kemp called in the crew chief, asked who had done the modification. The crew chief, Sergeant Thomas Riley, stood there trying to decide whether to lie or tell the truth. Finally told the truth, said Technical Sergeant Zaremba had done it. said Zaremba had modified most of the aircraft in the group, said the modifications were keeping pilots alive. Kemp asked how many aircraft had been modified. Riley said he wasn't sure, maybe 50, maybe more. Kemp found Zaremba in the maintenance area 2 hours later. Zaremba was working on a different B-17, replacing a damaged engine mount. His hands were black with grease. His coveralls were stained with hydraulic fluid and engine oil. He saw Kemp coming, knew what was about to happen, figured he was about to be arrested. Kemp identified himself, asked Zaremba to explain the modification. Zaremba expected threats, expected to be placed under guard. Instead, Kemp pulled out a notebook, started taking notes, asked Zaremba to walk him through the problem, the solution, the testing, the results. Zaremba talked for 20 minutes, showed Kemp the routing, showed him the splice, showed him maintenance records documenting which aircraft had been modified and which hadn't, showed him the statistics. Kemp looked at the numbers: 9 losses in January, 2 in February, 0 in March. He asked Zaremba why he hadn't reported this through official channels. Zaremba said he had tried. His commanding officer wouldn't listen, said the problem was battle damage, said field mechanics didn't have authority to investigate engineering problems. Kemp asked if Zaremba had documentation. Zaremba gave him the notebook, spiral-bound, water-stained, filled with pencil sketches and pressure calculations and installation notes. Kemp took the notebook, said nothing about regulations or unauthorized modifications, said nothing about charges or court-martial. He just thanked Zaremba for his time, left Station 174 that evening, flew back to headquarters. Zaremba waited for consequences, expected military police, expected formal charges, expected to lose his stripes. The consequences came, but not the ones he expected. On March 15, 1944, 8th Air Force issued Technical Order 0120EG589, mandating immediate modification of oil line routing on all B-17F and B-17G model aircraft in the European theatre. The order provided specifications nearly identical to Zaremba's modification, engineering drawings showing the revised routing, parts lists specifying the union fittings and additional tubing required, installation procedures, testing requirements. The order was marked urgent. All aircraft were to be modified within 72 hours. The order credited field maintenance analysis and engineering review for identifying the issue. It did not mention Zaremba by name, did not mention Station 174, did not mention the unauthorized modifications that had been happening for 2 months. Within 6 weeks, every B-17 in England had the modified oil line. The modification spread to other theatres, Italy, Pacific, anywhere B-17s were flying. The impact was measurable and immediate. From April through August 1944, the 8th Air Force flew 87,240 bomber sorties, lost 1,283 B-17s to all causes. Of those, 14 were lost to engine fires following combat damage, 14 aircraft out of 1,483 losses. In the same period, in 1943, before the modification, engine fires had accounted for approximately 90 aircraft losses. The improvement saved an estimated 840 lives based on average crew survival rates and assuming similar combat intensity. But Frank Zaremba never received official recognition. No Distinguished Service Medal, no Legion of Merit, no commendation, no mention in any report that bore his name. The technical order gave credit to engineering analysis. The official history of the 8th Air Force, published in 1945, mentioned improved engine reliability in 1944, but attributed it to better maintenance procedures and improved pilot training. Years later, when military historians researched B-17 modifications, they found references to field-developed solutions and maintenance innovations, but no individual attribution. The paper trail led nowhere specific. The technical order existed, the modification was documented, but the origin story had been sanitized, made generic, made official. Frank Zaremba stayed in the Army Air Force until 1946, worked as a maintenance supervisor at various bases, MacDill Field in Florida, March Field in California, mustered out as a master sergeant with 7 years of service, returned to Pennsylvania, opened a garage in Scranton, fixed cars and trucks for 35 years. When people asked about the war, he said he was a mechanic, kept planes flying. That was all. He never mentioned the modification. In 1982, a researcher writing a technical history of B-17 modifications found a reference in a Station 174 maintenance log to Zaremba's oil line mod. The log had been sitting in a warehouse in Pennsylvania for 37 years. Nobody had looked at it. The researcher, a retired Air Force colonel named Richard Martinez, became curious. Took him 3 years to track down Zaremba through veteran registries. By then, Zaremba was 67 years old, retired, living in the same house he'd bought in 1947. Martinez called him on the phone, asked him about the modification. Zaremba was quiet for a long moment, then confirmed it, said it wasn't complicated. The oil line was too close to hot components. Moving it made sense. Martinez asked if he'd kept any documentation. Zaremba said he had a notebook somewhere. Think he still had it. Martinez drove to Pennsylvania, met Zaremba at his house. Zaremba found the notebook in a box in his garage, spiral-bound, water-stained, pages yellowed with age, filled with pencil sketches and pressure calculations and installation notes. Everything was still legible. The notebook became part of the Air Force Museum collection in 1985. It sits in the archives at Wright-Patterson Air Force Base in Ohio. Most people who visit the museum never see it. It's not on display, just paperwork in a box. But it's there. Frank Zaremba died in 1998 at age 83. His obituary in the Scranton Times-Tribune mentioned his World War II service as an aircraft mechanic with the 8th Air Force. It did not mention that he'd saved approximately 840 lives with a splice fitting and 11 inches of steel tube. Did not mention that he'd solved a problem that engineering teams had been unable to fix. Did not mention that he'd done it without permission and made it work anyway. That's how problems actually get solved in war, not through committees or official channels or engineering review boards, through sergeants who see what's wrong, figure out what's needed, and don't wait for authorization to save lives. Through mechanics who care more about keeping pilots alive than about following regulations. Through people who understand that sometimes the right thing to do is also the thing that could get you court-martialed. The modification still exists. Modern restorations of B-17 aircraft use the revised oil line routing. The warbird community knows about it, knows it as the standard configuration. Most don't know where it came from, don't know about Zaremba, don't know about the 50 unauthorized modifications that forced the Air Force to make it official. But the pilots knew, the ones who flew modified aircraft, the ones who feathered damaged engines and didn't explode. Some of them knew something had changed, knew their aircraft were different somehow. A few asked their crew chiefs, got told about the rerouted oil line, got told to keep quiet about it, and they did, for decades. Now you know too.